Hello again and welcome back. We covered pretty much everything that is necessary on the content part of 6.2. All that is left now is some exercises to solidify your understanding. For that purpose, let's begin with a review. A summary rather. Here in this table, let us summarize the definitions of the trigonometric ratios. Sine, cosine, and tangent are defined by opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent respectively. And cosecant, secant, and cotangent are their reciprocals respectively. Now, what kind of problems am I going to key on? Like example 2. Example 1 is not really worthy of our time. Example 2 is a little bit more interesting. Cosine value is given. Cosine of alpha is 3/4. We have to find out the other 5 trig values. Now, cosine of alpha is 3/4, so secant of alpha is 4/3. It's 1 over cosine, so it's easy. The other 4, on the other hand, will require some thinking. Of course, pictures will help. What is the other kind of problem that I'm going to key upon? Solving a right triangle. Example 3. Solve triangle ABC shown in figure 7, which I'm going to show you in a moment. Basically what we have here is one side and one angle, and we have to find out the other sides. We have a little bit more control over my notebook where I can write and highlight and things like those. So let's get away from our textbook and then reproduce the same thing in my notebook. And here we go. Cosine of alpha is 3/4, and find the other trig values of alpha. Oh, actually, I forgot one thing. Okay, sorry about that. It is really necessary to specify the angle is an acute angle, an angle between 0 and 90 degrees, or in radian measure, between 0 and pi over 2. Otherwise, everything will break down, and that's going to be an important topic that we'll discuss in the next section. Now, find out the other trig values. And this kind of thing can be done with a picture. And here is the picture. Alpha went to the standard place, the lower left-hand side. And then in the right-hand side, we have a right angle. And the top angle is going to be actually pi over 2 minus alpha, because the internal angles of a triangle must add up to 180 degrees in DMS measure, or pi in radian measure. Okay, we have that, and then we labeled hypotenuse as 4 and adjacent as 3. That's rather natural because cosine is defined by adjacent over hypotenuse, and that ratio is 3/4. So why don't I just draw a right triangle with adjacent 3 and hypotenuse 4. Now what's left is the height. The opposite. We don't know that, so let's name it x, and let's find out x. How do we do that? Pythagorean theorem. 3 squared plus x squared is hypotenuse squared, that's 4 squared. From this we can find out x squared. X squared is 4 squared minus 3 squared, so 16 minus 9, that's 7. Taking the square root, we have x equals the square root of 7. We don't have to worry about the negative square root of 7 because we are dealing with a geometrical quantity, so everything is positive. So put square root of 7 in place of this x here, and we can find out all the trig values because now opposite is positively identified. It is square root of 7. For example, sine is opposite over hypotenuse, so it's square root of 7 over 4. Tangent, cosecant, everything follows from this triangle. So once you have triangle, you get everything. Okay, let's move on to the next example. This time we are solving a right triangle. This time not the trig value, but the angle is given. And one side is given. In this particular case, hypotenuse is given, and that's 12. And we have to find out the other sides, A and B. Okay, what is A? We can use cosine because A over 12 adjacent over hypotenuse is cosine. How do you find out B? We can use this sine function. B over 12 is opposite over hypotenuse, so that's sine of 30 degrees. So cosine of 30 degrees is square root of 3 over 2. So after a little bit of algebraic manipulation, you can find out A value, 6 square root of 3. And then if you plug in sine of 30 degrees as 1/2, then you can find out B value. That turns out to be 6. You can do something similar in other situations too. I mean, in this case, hypotenuse was given, so you had to use sine and cosine to find out the other sides. But for example, if adjacent is given, you'll have to use tangent to figure out the opposite, and then cosine to figure out this hypotenuse, things like those. Okay, we went through elementary examples, so are we ready to go on to a little bit more real-life application problems that use those elementary examples? Well, here's one. Finding out a height of a tree. And this is a realistic example, as you see. Finding out the height of a tree is not an easy thing to do. To climb up the tree is one thing, and then finding out the height using a tape measure with all this obstruction from the branches, forget it, that's impossible. It's much better to use trigonometry. Here's a picture, and please recognize that we end up with a right triangle. Determining the length of a shadow is no big deal. You can simply measure from the ground, so that's much easier. And then finding out the angle is even easier thing to do. All you have to do is look up this sun using some special equipment to measure the angle, which are kind of ancient actually. Even ancient Greeks used to this kind of things in navigations and measurement in all kind of situations. So okay, we have 25.7 degrees as the angle of elevation and 532 feet as the length of the shadow. So we have the angle and adjacent. How do we find out the opposite? The height is the opposite in this case. What kind of trig function do I use? Opposite over adjacent is tangent. So we use this. Tangent is equal to h over 532. Flip this denominator to the other side, we get h equals to tangent of 25.7 degrees times 532 feet. Punch in the calculator and we have the answer. Make sure your calculator is in degree mode. We end up with 256 feet. It's a big tree. Must be coastal redwood or something like that. I know some trees grow over 300 feet, over 100 meters. Okay, let's move on to the next problem. Again, I took this problem from our textbook. And this problem is a little bit more interesting in that we don't have just one right triangle, but we have two. The height of this flagpole is 60 feet tall, but it is not a side of one right triangle because, you see, add up those two angles and we have 32 degrees, and that's big triangle is not a right triangle, so we cannot really use all kind of trigonometry. Instead, we have two right triangles with angles 18 degrees and 14 degrees respectively, as we see in this picture. Simplified picture. This one versus that one. We no longer need the top one. We have blue triangle with 18 degrees and red triangle with 14 degrees. And I made additional labeling A and B for the top portion of the flagpole and the bottom portion of the flagpole. I hope everybody can see that we have A plus B is equal to 60 from this simplified picture and the new labeling. Does it help? It should. We have an equation. The problem, we have equation with two unknowns, A and B, and neither of them is x. A bit of a problem, but not something that is insurmountable, because we have two triangles. We have two unknowns here, but we have two triangles, and each triangle will take care of one unknown. Let's see. If we use common sense, A will be coming from the blue triangle. That's because A is part of the blue triangle. And B will be coming from the red triangle because B is part of the red triangle. Well, that's a common sense argument. And indeed, it's true. What relation do we actually get? Here we go. A plus B is 60. And tangent of 18 degrees is A over x. Opposite over hypotenuse. And tangent of 14 degrees is B over x. Again, opposite over hypotenuse. With these two, we can find out what A and B are in terms of x, and we can plug those into the first equation. A plus B is equal to 60. What relations are we talking about? Solving for A and B, we get A equals x tangent of 18 degrees, and B equals x tangent of 14 degrees from the blue relation and the red relation, respectively, which ultimately came from the blue triangle and the red triangles. So what do we have? A plus B is equal to 60. Plug those blue and red in appropriate places according to my color coding here. And we have, well, x tangent of 18 degrees plus x tangent of 14 degrees is equal to 60, approximately, of course. From this, we can solve for x. That's easy now. Plug in those values by punching the calculator. Tangent of 18 degrees is 0.32 something. Tangent of 14 degrees, 0.24 something. And after algebraic manipulation, we have 60 over that figure. We end up with 104.5 feet. Okay, we have a little bit of time left, and both of our examples we did were tangent functions. So let's talk about something else, and that something else is problem C. The elongation alpha of a planet is the angle formed by the planet, the Earth, and the Sun, as you see in this picture. And it reaches a maximum when we have the right triangle, as you see in this picture. And the maximum elongation for Venus is known to be 46.3 degrees. And find out the distance between Sun and Venus in terms of the astronomical unit, and later on in terms of miles. How do we do that? Well, we have to use this trigonometry, and please note that hypotenuse is 1 AU, 1 astronomical unit, or 9.3 or 93 million miles. So what do? Hypotenuse and then opposite. So we use sine function. Sine of the distance between Sun and the Venus and the distance between Sun and the Earth is sine of alpha. So the distance between Sun and Venus will be the distance between Sun and Earth times sine of alpha. And the distance between the Sun and Earth is 1 AU. So 1 times sine of 46.6. So we end up with 0.7 something astronomical unit. Just punch in the calculator. Make sure your calculator is in degree setting. Then sine of 46.3 degrees will give you 0.72 something. Now, 1 AU is 93 million miles approximately. So multiply 93 million and you're going to end up with 6.72 times 10 to the 7th power, so 67.2 million miles.